irreducible, you just do a quick communication check. You start at a point and you say, okay, can I get to any other point and back from this point? And if you can get to any other point and back, well, then you know that you could get from any of the original points you were at back to them, because you just take the path you took to get to that state, and then you go back to one, and you go back to that state again.
Right, right.
So you know that there's some path between every state at that point. Once you start at one state and you say, can I get to every state and back?
Right, okay. Yes, I think I understand what you mean. So if you have, I think what you're trying to say is,
you want to use this?
Yeah. I think what you're trying to say is, so let's say if I have a way of going from 1 to 2 and then from 2 to 3. So let's say if I have a way, and by the way, so I think what you're trying to say is if I could pick any one state, say 1, and I can get to 3, then it means that this whole system is irreducible because
you need to be able to get back to 1.
I need to be able to get back to 1.
If you can get to 3 and back to 1, then the whole thing communicates.
Because it means that I have a way of going from 2 back to 2, because it's just an extra step.
Exactly.
To go from 1 to 2.
Exactly.
Right.
So if you've gone from 1 to 2 and then all the way back to 1, you know that taking one extra step takes you back to 2, and therefore you've gone from 2 back to 2.
Right.
And therefore you know that every single state communicates with every other state.
Right. You've mapped out the path
essentially
to get back to the original state. So it's just shifting your
loop by
by 1. Yes. Thank you. Okay.
Yeah. So that's the easiest way to check for irreducibilities. You just start at one state. You say, can I visit every state and get back to where I started?
Okay.
Can you get back home?
Is there some property in the transition probability matrix that can help us to look for irreducibility?
Not really.
No. Okay.
I mean, obviously, if every single element is filled, then yes.
Okay.
You're guaranteed, because you can consider the fact that you can go from any state to any other state directly.
Right.
But if you don't have that case, usually it's not. And oftentimes, after you've looked at a couple of these transition probability matrices, your brain is much quicker at recognizing what is and isn't irreducible Markov chain.
Right.
When you first start out, it's not always that clear.
Okay. So if a transition probability matrix is non-zero in every entry,
it's definitely
then it is definitely irreducible.
Yeah.
But that is a very strong condition. and it seems like what you're saying to me is many of the more interesting cases are ones where there are 0 entries, but it's still irreducible.
Yeah, exactly.
It's just it's not immediately obvious.
It's not immediately obvious.
Right.
I mean, obviously as well, if you can move, if it's a chain sort of structure. So if you can have, let's say, there's 10 possible states, and you can go from 1 to 2, and you can go from 2 to 1 or to 3, and then from 3 to 2 or to 4, then that's pretty easy to see. You could draw a chain all the way up to 10 and then back down to 1, right? Pretty much directly like this one, right? So from 2, you can go to 1 or to 3, and it's pretty easy to see based off of this that there's an easy sort of chain you could follow.
Yeah, I think what you were trying to say there was if you can go from 1 to 2, then you can treat this as kind of like one.
You can treat that as
one state, and then if you can show that this state can
you can
go to 3,
absolutely,
then that's irreducible because like this is another state right here.
Yes.
Right. And so if you can go from this state to this state, then you've shown that it's irreducible.
Exactly.
Right.
This state to this state and back.
Right.
You need to always go back. That's the idea.
Right. Okay.
And that's actually a nice thing you can do with Markov chains. If you have a bunch that communicate but not with each other, you can split it apart into separate chains.
Right.
Or consider all of them one state. Because, like I said earlier, the technical term, it introduces a partition where they're all equivalent. It's an equivalent partition of the space.
Right.